For this video, we're checking to see when the function f of x equals 6 divided by the quantity x squared plus 3 is concave up, where it's concave down, and if there are any points of inflection. So the first thing you might look for if it occurs to you is just to see if there are any places where this function is actually not continuous. And so you're looking to see what x value could make this x squared plus 3 0, and there isn't one. If you square a number, the least it will be is 0, because if you square a positive or a negative, you get a positive number. If you square 0, you get 0. So 0 would be the least, plus 3 is definitely positive, so there is no divide by 0 for this function. So it is a continuous function. So I'm going to go to the first derivative, and you have choices here. You could use the quotient rule as long as you remember that the derivative of 6, a number is 0, and it cancels out the part that you wouldn't need. Or you could think of it as the chain rule. So this would be like a 6u to the negative 1, which is what I'm going to do. So when I take the derivative, I get a negative 6. My u is x squared plus 3 to the negative 2 times the derivative of the inside, a positive 2x. If I rewrite this, negative 6 times 2x is a negative 12x, and that will be divided by the x squared plus 3 squared. It's squared, but we have a negative exponent, so that throws it to the denominator. To take the second derivative, I am going to use the quotient rule. So that will be the denominator, x squared plus 3 squared, times the derivative of the numerator, a negative 12x. I'm sorry, negative 12. Minus the numerator, so plus 12x, times the derivative of the denominator. This is like a u squared, so it'll be times 2, leave my inside function alone, times the derivative, and this is to the first, times the derivative of the inside, a 2x, all over my denominator, x squared plus 3, which was squared, is now squared squared, which is to the fourth. If you look at this to simplify, which I would definitely do right now, you should see that there's an x squared plus 3, at least one, there's 2 right there, 1 right here, and 4 right here, in each part of this. So what I'm going to do is cancel out one of them. So my second derivative will equal, and I'm going to bring the negative 12 to the front, x squared plus 3, now to the first, there were 2, plus, and then this is a 12x times 2 is 24x, times 2 is a 48, x squared, and I've canceled out my 1, over x squared plus 3, now to the third. So if I work to simplify my numerator, this would be a negative 12x squared minus 36 plus 48x squared. So combining like terms, I have a 36x squared minus 36 in my numerator. I can factor that out. It's a 36 times x squared minus 1, or 36 times x plus 1, x minus 1, over my x squared plus 3 to the third. And this is my second derivative with respect to x factored. So looking at it now, I want to know when it will actually be equal to 0 and when it will be undefined. Well, I already know x squared plus 3 can't equal 0. It's always positive. So when I cube it, it's going to remain positive. So my denominator will always be greater than 0. So my second derivative is never going to be undefined. If I look in my numerator, I can set that equal to 0 to figure out when my second derivative is actually equal to 0. So if I set x plus 1 equal to 0, I get x equals negative 1. Positive 1 for x minus 1. So I have two possible points of inflection. So I'm going to put them on a number line, negative 1 and 1, and I'm checking the sign of my second derivative. Now, I know that the denominator is always going to be positive, so I can basically just ignore it when I'm checking this. So I'm going to ignore that, and I'm only going to plug into these two because, again, this is positive, so it's not really affecting the sign. The sign is going to be affected by these two factors right here. So if I pick a number to the left of my negative 1, let's say negative 100, negative 100 plus 1 is definitely negative, and a negative 100 minus 1 is still negative. Negative times a negative is positive. and my function is concave up on this interval. If I pick a number between -1 and 1 like 0, I have a positive times a negative is negative, concave down on that interval. Number to the right of 1 like 10, 10 plus 1 is positive, 10 minus 1 is still positive, positive times a positive is positive, concave up on that interval. So I know that f of x is concave up from negative infinity to -1 and from 1 to infinity, and I know that because f double prime of x is greater than 0. F of x is concave down on the interval from -1 to 1, and I know that because f double prime of x is less than 0. And since the signs of the second derivative changed, I know that x equals -1 and 1, let's move this up, are points of inflection. The justification would be that f double prime of x changes signs. And that would be the end of that example.